Last episode, activation functions. Sigmoid, ReLU, GELU, the nonlinearities that make deep networks work. Back in episode 74, I mentioned 3 types of machine learning: supervised, unsupervised, and reinforcement. We covered the first 2 in full. The third one never got its episode. Until now. Hi, I am Mahaz. This is Reinforcement Learning Basics. No labels. No clusters. An agent that learns by trying things and getting rewarded or punished, from slot machines to a self-navigating grid. Supervised learning. Here is the data. Here is the correct answer. Learn the mapping. Unsupervised learning. Here is the data. Find the structure yourself. Reinforcement learning is different from both. There is no correct answer given up front. There is an agent, an environment, and a reward signal. The agent takes an action. The environment responds with a new state and a reward, a number saying how good or bad that action was. The agent's only goal: maximize total reward over time. It learns entirely through trial and error, through consequences. This is how you train a robot to walk, an AI to play chess, or a recommendation engine to learn what keeps you engaged. Start with the simplest possible reinforcement learning problem: the multi-armed bandit. Picture a row of slot machines. Each one pays out with a different, unknown probability. You have a limited number of pulls. Which machine do you play? You do not know the payout rates in advance. You only find out by pulling levers and observing what happens. This creates a tension. Do you keep pulling the lever that has paid off before? Exploitation? Or try a different one that might be even better? Exploration? Every reinforcement learning problem contains this same tension. The multi-armed bandit isolates it in its purest form. 3 strategies for balancing exploration and exploitation. Epsilon-greedy. Most of the time, pull the lever with the best average payout so far. A small fraction of the time, epsilon. Pull a random lever instead, just to keep learning. Upper confidence bound, or UCB. Prefer levers you are uncertain about. Add a bonus to each lever's estimated value based on how rarely you have tried it. Uncertainty itself becomes worth exploring. Thompson sampling. Keep a probability distribution over each lever's true payout rate. Sample from each distribution and pull whichever lever sample is highest. Naturally balances explore and exploit. In practice, Epsilon-greedy is simplest to implement. UCB and Thompson sampling usually converge faster and are preferred in production systems like ad placement and A/B testing. Bandits have no state. Every pull is independent. Most real problems are not that simple. For those, we need a Markov decision process. An MDP has 4 parts: states, where the agent can be; actions, what the agent can do in each state; rewards, the number the environment returns after each action; and transitions, the rule for how the state changes given an action. The Markov property: the future only depends on the current state, not the full history of how you got there. That assumption is what makes the math tractable. The agent's job is to learn a policy, a rule for choosing actions in each state, that maximizes total future reward. The Bellman equation is the heart of reinforcement learning. Define the value of a state as the expected total future reward if you follow your policy from there onward. The Bellman equation says, the value of a state equals the immediate reward, plus the discounted value of whatever state you land in next. The discount factor, gamma, between 0 and 1, controls how much the agent cares about future rewards versus immediate ones. This recursive relationship, value now depends on value later, is what every reinforcement learning algorithm is built on top of. Q-learning turns the Bellman equation into a learning algorithm. Instead of the value of a state, Q-learning tracks the value of a state action pair, called Q of S, A. How good is it to take action a while in state S? Store these values in a table, 1 row per state, 1 column per action. Start the table at all zeros. The agent knows nothing yet. The update rule: after taking action in state S and observing reward R and next state S prime, nudge Q of S, a toward R plus gamma times the best Q value available from S prime. New Q equals old Q, plus a learning rate alpha, times the difference between the target and the old estimate. Repeat this over thousands of episodes, and the table converges to the true optimal values. Let's watch this happen. A simple grid world. The agent starts top left, the goal is bottom right, and there is a penalty tile to avoid. Early on, the agent moves almost randomly. It has no idea what is good or bad. It bumps into the penalty tile, gets a negative reward, and updates its Q table. After a few hundred episodes, the Q values near the goal start propagating backward through the grid. States near the goal become clearly more valuable than states near the penalty. By the end of training, the agent's path is direct. It goes straight to the goal, avoiding the penalty every time. Nobody told it the shortest path. It discovered it. One detail that makes this work well: epsilon decay. Early in training, the agent should explore a lot. It knows nothing, so random actions are as good as any. Set epsilon high, close to 1. As training progresses and the Q table becomes more accurate, exploring randomly wastes time. Gradually shrink epsilon toward a small value, so the agent exploits what it has learned. This explore then exploit shape. High epsilon early, low epsilon late. Shows up in almost every practical reinforcement learning system. Your first Q learning agent. About 15 lines of Python. Initialize a Q table of zeros, sized states by actions. Set your learning rate alpha, discount gamma, and starting epsilon. For each episode, reset the environment. While not done, with probability epsilon pick a random action, otherwise pick the action with the highest Q value for the current state. Take the action, observe reward, and next state. Apply the Q learning update rule directly to the table. Move to the next state. Decay epsilon slightly after each episode. That loop, repeated for thousands of episodes, is the entire algorithm. No neural network required. That upgrade is next episode. Recap. Reinforcement learning in 6 ideas. Agent, environment, reward. The agent acts. The environment responds with a new state and a reward. Multi-armed bandit. The purest form of the explore-exploit trade-off. Epsilon-greedy, UCB, Thompson sampling. 3 ways to balance exploring and exploiting. Markov decision process. States, actions, rewards, and a policy the agent is trying to optimize. Bellman equation. The value of a state equals immediate reward plus discounted future value. Q-learning. Learn state action values directly from experience. No model of the environment required. Challenge. Apply this to Gymnasium's frozen lake environment. Train for 10,000 episodes with epsilon decay. Plot your win rate curve. Post it in the comments. Reinforcement learning is not magic either. It is trial, error, and a table of numbers that slowly gets less wrong. Every action nudges a value estimate closer to the truth. Enough nudges, and optimal behavior emerges from the table on its own. Next up, deep Q networks. We replace the Q table with a neural network, and reinforcement learning meets everything you learned in the deep learning series. Subscribe. The Deep Q Networks episode drops very soon. Drop your frozen lake win rate in the comments. See you in episode 114.